Alright, let's see how we differentiate our trig. Now, in order to do this, I need to look at some limits, because we'll do it from first principles, so we need to know some limits. Now, obviously from our graph, we know the limit as sine x as x approaches 0 would be 0, cosine would be 1, tan would be 0. They're fair enough. So how I'm going to derive this is by playing with the areas of some shapes. So I've drawn in a sector here, radius 1, angle at the centre is x, and that's in radians. And I know that area of the sector would be greater than the area of that triangle. Okay. But if I was to draw in a tangent at A and create a right angled triangle, I know that that area would be bigger than the sector. So I'm going to be able to trap the area of the sector between these two triangles. So area of AOC, half AB sine, well in this case x. Area of the sector, half r score 1 squared x, and half base times height for the other triangle. Now the height of that triangle we could work out would be the tan of whatever x is, because it's a right angle triangle, opposite over adjacent. Alright, well they've all got a half in it, so that tells me that the size of that angle is somewhere between its sine and its tan. Now if I divide all three by sine x, I come up with this relationship, that x on sine x will always be in between 1 and the reciprocal of the cosine of the angle. That now allows me to create another limit, because I'm going to need this x on sine x ratio. Will have to be in between 1 and 1. So we said the limit for cos was 1. Well, if it's in between 1 and 1, we've found the limit. So there's our limit. The limit as x approaches 0 of x on sine x is 1. I'm just going to do some examples here, because they do like these sorts of questions, working out these limits. And the key for the limit is the angle. It's sine x on x. So you need to make the, well, if I say sine x on x, I need to make the denominator the same as the angle. In this case, it's the numerator I'm going to make the same as the angle, because x on sine x is 1, but then of course so is sine x on x. It doesn't matter which way round I have it. In this case, it is the same. So not a problem, that's just going to be 1. But if I was to get something like that, then I've got x on sine 3x, then I want to make the numerator 3x, the same as the angle. And so to do that, I've got to balance it out. So I'll have a third of 3x. So the 3x on the sine 3x I know will approach 1, and so we get 1/3. So let's see how we're going to go and differentiate this function, sine x. And if we use first principles, limit as h approaches 0, sine of x plus h minus sine x all over h. Sine cos cos sine. If it's the sine, it's the sine. Now I'm going to manipulate this a little bit. So the cos x, if I pull that by itself, that would be multiplied by sine h on h. Not a problem, because I can find the limit as h approaches 0. Sine h on h, we now know that's 1. So, okay. Now the sine x, I've got cos h minus 1 on h. That's a problem, because we said, remember the limit as h approaches 0 of cos h was 1, so we've got 0 on 0. So we're going to have to manipulate that second bit a little bit more. So I'm going to rewrite cos h using the double angle ideas. Remember, cos 2 theta is 2 cos squared theta minus 1. Well, in this case, instead of 2 theta, I've got 1h. So double angle. So it becomes 2 cos squared half h minus 1. But then minus the other one we've got on top. I end up with minus 2. Okay, so that came from our double angle idea. Still can't substitute into that yet. But of course, cos squared minus 1, 1 minus cos squared is sine squared. So cos squared minus 1 would be minus sine squared. So that actually should be minus 2 sine squared. But as it's going to approach 0, it doesn't end up matter that I've made that little mistake, because now I can't sub into that because the angle is h on 2. The base is h on 2 if I put the 2 down there, but it's sine squared, it's not sine. Okay, so I can make a sine squared h on 2 to h on 2, but we didn't want sine squared on the top, we just wanted sine. So if I separate that out, I'm now okay. I can substitute into everything. Because the sine h on h, that'll become 1. The sine h on 2 on h on 2, that'll become 1. The sine h on 2 will become 0. So we end up with cos x times 1, sine x times 0, cos x. So to generalise that one, if we're finding the sine of some function, we'll end up differentiating the angle, putting that out the front, and the sine changes to cosine. The angle does not change. But remember, this all works because we're going back to how I defined that limit. X was in radians. So the angle measure, whenever we're doing calculus and trig, it's got to be measured in radians. All right, let's see what happens with cos x. Now, fortunately, now I know that when I differentiate sine and get cos, I can do a little bit of manipulation and work this one out easier than the last one, because the cos I could rewrite as sine of pi on 2 minus x. And now I can differentiate that, because we know how to do that one. Differentiate the angle, I get minus 1. The sine changes to cos, and the angle doesn't change. But the cosine of pi on 2 minus x is sine x. So to generalise that one, if I've got the cosine of some function, differentiate the function, that'll go out the front, but the cos will go to minus sine. And again, the angle does not change. All right, let's see what happens with tan. Tan I'll rewrite as sine on cos, because I now know how to differentiate both sine and cos. So we just got to use a quotient rule. Square the bottom, cos squared x. Write down the bottom, cos x. Diff the top, sine goes to cosine. Minus, write down the top, sine x. Diff the bottom, cos goes to negative sine. So on the top of the fraction, I end up with cos squared plus sine squared, which is, of course, 1. So we have the reciprocal of cos squared, which is sec squared. So you differentiate tan, you get sec squared. So to generalise that one, again, differentiate the angle. That goes out the front. Tan changes to sec squared. The angle does not change. All right, let's do some examples. So y equals the sine of x cubed. Okay, the angle is x cubed. Differentiate the angle, 3x squared. Sine goes to cosine. The angle does not change. So 3x squared cos of x cubed. Tan of 1 on x. Okay, we differentiate 1 on x, we get minus 1 on x squared. So minus 1 on x squared, tan goes to sec squared, angle does not change, it's 1 on x. The log of cos x. Okay, it's a log function that we're differentiating now. Differentiate log, derivative on function. Okay, so the function is cos x. Differentiate cos x, you get, so derivative on function, we get minus sine x on cos x. But sine x on cos x is, of course, so we get minus tan x. Now, remember, that actually means tan x all to the power of 5. It's just the way we wrote the notation. So we've got to use our chain rule. Bring down the power, lower the power, diff the inside. So the inside would be tan x, differentiate tan x, sec squared x. So we've got 5, tan to the power of 4x, sec squared x. Differentiate the angle is e to the x this time. Derivative of e to the x is e to the x, world's easiest derivative. That goes out the front. Differentiate cos, cos goes to minus sine, and the angle doesn't change. So we get minus e to the x sine e to the x. Okay, time to play.